This is a presentation on a couple of mixed signal VLSI systems. One is going to be a phase log loop and the other one is going to be an analog to digital converter. So first, the phase log loop, this is the block diagram of the system. It is what is called a charge pump and current starved inverter voltage control oscillator based phase log loop. So first, let's talk about a typical application, which is this phase log loop are very popular in the VLSI chips to do clock skewing or frequency synthesis. We have here in this block diagram the depiction of a frequency synthesis application. So here we have some frequency for FSC, and here we're getting that frequency multiplied times 4 as 16 times FSC. So it's in this configuration with this type of feedback, the phase log loop becomes a closed feedback control system where the error signals are based on the phase difference of these two input signals. So we want the phase log loop is going to want to keep this error at 0 or the signals in phase. And here we have a 2-bit counter which is dividing the frequency times by 4, dividing the frequency by 4. So if the system wants these two signals to be in phase, the only way that can happen is if the two signals have the same frequency. Therefore, if we want these two signals to be the same frequency, i.e., we want this frequency to be 4 FSE, then since we're dividing by 4, then this frequency has to be 4 times this frequency, which is 16 FSE. And that's how we achieve the frequency synthesis. So how does this work? What is the signal progression or the signal train through these blocks? So the phase detector is going to generate pulses that are which has a width, a time width that is the same as the difference in phase of the two signals. And depending whether they are lagging or leading with respect to each other, we're going to get what is called an up pulse or a down pulse. Now, these pulses are both positive going pulses. These are digital signals from 0 to 1, but they're going to be driving this analog circuit, which is a charge pump. Essentially, these are current sources that are going to either charge a capacitive network, which is a filter, or it's going to be discharging that capacitor network. Now, since this network is capacitive and we are driving it with current sources, with current pulses from current sources, we're putting in a current, but here we are utilizing the voltage at the same node that the current is coming in or being drawn out. So since the voltage across the capacitor is the integral of the current, we're going to be getting voltage ramps up or ramps down at this node over here, which is the same as this one. It's just that here, this is current in or out, but this is voltage up or down at a ramp rate. Because the integral of pulses in a capacitor, the integral of pulse currents are ramps. The integral of a pulse is a ramp, and the voltage here is the integral of the current. Then that goes into the VCO as a control voltage that is going to have some linearity about it. And as we'll see, if the voltage goes up, we're going to get a faster frequency out of the VCO. If the voltage goes down, we're going to get a slower frequency. And that's how this automatic feedback control system works. So next, let's look at each of the blocks. First, the phase detector. And this is how the phase detector looks. It's basically a latch-based phase detector. We see a couple of latches with additional logic and feedback. And my description has been and is going to be qualitative in nature, not so much analytical, because what I want is for you to be able to construct this circuit in a VLSI design system like Cadence Virtuoso. So I want to explain, give you the schematics, and tell you what the particular and the details of those schematics are. So in this case, when we see these numbers by this gate, so we have this a number of 2-input AND gates, we have a 4-input AND gate, and we have a 3-input, a couple of 3-input AND gates, and a number of inverters. These are NAND gates as well. It's just different symbology. So when you see these numbers, outside of the gate, what is relating to is the relative size of the P transistors and the N transistors in terms of the minimum size of the transistors. So these transistors, let's take this gate here. Both the P channel and the N channel are going to be minimum width transistors or minimum channel length transistors, which for the technology that we have been using is 150 nanometers. But the size of the transistor or the channel width is going to be 8 times 150 nanometers for the N channel, and for the P channel is going to be 16 times 150 nanometers in our case. So that explains the numbers for this specific logic-based diagram, because it changes a little bit when we're looking at transistors, okay? Then, the other thing to explain here, okay, because again, this circuit we know that is going to be producing up or down pulses that are going to be the same width in time as the difference in phase between these two signals. The other thing to explain is these bubbles at the inputs of the gates. We know that an AND gate has the number of input of P channel transistors in parallel and the number of input of N channel transistors in series pulling down. So the bubble here refers that input is specifically connected to the transistor that is closest to the N channel that is closest to ground. That is specific input. And that's what the bubble means for all these different gates. So again, it's a very straightforward logic diagram to implement once you implement the gates and the inverters and take into account what these numbers mean. Then we have the charge pump. The charge pump is given in these two diagrams here. That is the entirety of the charge pump. So first, we see the positive current source here and the negative current source. So this is going to be charging. This current source is going to be used to charge the capacitive network at the output, and this one is going to be used to discharge the capacitive network at the output as controlled per the switches. This just connects the current source or disconnects them from the output, each one of them. So, and of course, they're driven by the up or the down pulse inputs to the charge pump. Also, this current mirror here generates the bias voltage for this N channel, this P channel current source or this N channel current source. The specific of the switch, which we have two of them, they're the same. So two instantiations of the switch is here. So we essentially have a transmission gate which implements the switch from the SW0 port to the SW1. You can see them here. And here you're generating the control for the transmission gate with some capacitance between these two inverters to generate some delay between the two signals. Now, when you see these two numbers, by a transistor, it means a different thing than when you see them by the gates. Here, what this means is that this N channel is going to have 2 times the minimum width. So in our case, our minimum width or minimum length of the channel is 150. So this is going to be 300 nanometers, and then this is going to be the length of the length of the transistor, or the width, the electrical width of the channel is going to be 40 times 150 nanometers. So that basically takes care of the charge pump. Then next is the filter or capacitive network. So here's an analog schematic of it. We have a series RC combination in parallel with another capacitor. But this is the actual implementation of it. Okay? So these two transistors implement the resistor. So we have they're essentially poor transistors that are resistive in nature with a large RDS on, and they are both on because the gate of the N channel is pulled to VDD and the gate of the N channel is pulled down to ground. But the length of the channel, or the width of the transistor, is larger than the length of the transistor or the width of the channel. So here we have, and since we're talking about transistors, these are multiples of our minimum size, which is 150 nanometers. So we also have the capacitors. So these two capacitors are the same. So they are them here. Okay. And again, here the size of the transistor would be 6 times 150 nanometers for the gate for the channel length or gate width, and 2400 times 150 nanometers for the channel width, or the transistor length, the geometric transistor length. So these are two very large transistors. And what you want to do when you implement it in the layout is use fingers for the layout, the appropriate number of fingers. So these two together, you get, for the overall thing, you get some type of a square reasonable aspect ratio. So you have to see, what that number of fingers needs to be. And of course, that the layout tool will generate the transistor automatically, given, when you tell it how many fingers you want for the transistor, and you can change that dynamically in the tool. So that's a straightforward implementation of the filter capacitive network. And remember, when you are inputting a current in or out, or input a current or extract charge, a current coming out of this network, what you get respectively are voltage ramp up or down. If you're putting current, you get voltage up, ramp up, which is the integral of that current pulse. And if you get a negative current pulse, so getting charge out of the network, you get a ramp down, which is the integral of that negative current pulse. So this is the output of the filter that goes into the voltage controlled oscillator. So here's the voltage control oscillator. Is a number of current starred inverters. So 13 of them, 13 stages with this feedback. So that makes up an oscillator. So remember, you have to have an odd number of inverter stages to have oscillation. And you are going to then you just have this buffer here, okay, this buffer here. So you can see the inverters made out of these two transistors in the middle. That's an inverter. Input, output of the inverter. But then we have these two additional transistors on top, one on top and one in the bottom. Those are resistors. Those are variable resistors. You can see the sizes of this of the transistors. In this case, we have one here, so it means that the transistor gate size or channel length is 150 nanometers, and the channel width would be 16 times 150 nanometers, and so on with these other numbers. Same thing. So the way that this works is that we have this circuit here, which is going to symmetrically mirror the voltage. So if VDD here is 1.8 volts and this control voltage is 1.7, essentially 0.1 volts below VDD, then the voltage here is going to be 0.1 volt above VSS. That's the job of this circuit here, okay? And then with that voltage, what we can do is vary the voltage at the gate of these transistors, and they become essentially voltage controlled resistors or variable resistors. As the resistance goes up, we drop more of a voltage across the source to drain of these transistors, effectively reducing the VDD that the inverter sees. And we know that the propagation delay of the inverter is proportional to VDD. So if we make the VDD smaller from this node to this node, so the voltage which acts as a supply for the inverter, this is the supply voltage that the inverter sees. If we make that voltage smaller, then the delay of the inverter is going to increase. If the delay of the inverter increases, then the frequency of the inverter decreases and we get a lower frequency. As this voltage goes up, then we turn on more of this transistor and this one as well, and then the resistance becomes smaller, so we drop less of a voltage, because remember, the current through here, being MOSFETs, they're based on current sourcing. So we drop less of a voltage, and then here, and then the effective supply voltage that the inverter sees is much higher. And when that supply voltage is higher, then the delay will be lower, making the frequency of the oscillator higher. So you will get some type of transfer curve that is going to be sort of like an S, not perfectly linear. There's going to be like a tilted S, but in the middle there will be a very reasonable linear operating region of control of frequency output versus control voltage. And that's how the oscillator works. And when you put it all together, then it works. You have the whole PLL that works as I described at the beginning in the first slide. Okay, so the next system that I wanted to discuss was an analog to digital converter. There are many architectures of analog to digital converter, mainly three that are used a lot. This is what is called a flash digital analog to digital converter. And they all have their advantages and disadvantages. The advantage of a flash A to D is that it's fast because you're essentially looking at the signal and comparing it to different segments of the range at the same time. The other one, kind of middle of the road, is a successive approximation register-based A to D converter. It's used a lot in microcontrollers. And then the other one is the delta signal modulation-based analog to digital converter. That one, you can get a lot of precision, but it's slow compared to the A to D that you can get higher speeds, but to get the precision, you have to replicate. You have to replicate a lot of these comparators, and you have to have a lot of these resistors. So it is fast, but it tends to be more expensive. So you don't tend to see more than 8 bits. If you needed something like a 24-bit analog to digital converter, then you would use something like a delta sigma modulator to get, and you would get a lot of resolution. Because again, you need 2 to the n resistors and 2 to the n comparators, which would be cost prohibitive for something like 24 bits. For this example, we're going to be looking at 6 bits, so we would need 64 resistors and 64 comparators. So this is the input side of the analog to digital converter, where we divide the voltage range between our negative reference and our positive reference. That is basically the span of the voltage that we want to convert. This very well could be ground and VDD, but it doesn't have to be. It could be something else. It could be a subset of the range, so you can actually get more resolution. And since we're looking at 6 bits, then we need 2 to the 6, which is 64. So we have 64 of this and 64 of the comparators. So by having this resistor ladder, and in this case 64 resistors, we are dividing the voltage range in 64 bins or buckets. And then we are comparing simultaneously the input signal with all of the different buckets to see where is that the signal becomes higher than the highest bucket, and that we know that we're close to what that analog voltage or digital voltage should be, because this is numbered from 0 to the highest digital value. Now this box here is just sampling, based on a clock, is sampling the analog input voltage, holding it in a capacitor and presenting it to the comparators all at the same time, so it can be compared to the different voltage ranges or voltage bins in the range. And what we get out of the comparators is what is called a thermometer type of output. That, let's say that the input is somewhere between, somewhere between this voltage and that voltage. So we know that that is somewhere is here. So what we're going to get out of the comparators over here are 1, 1, 1, but after that we get zeros over here. It's like a thermometer filling up as the voltage goes from 0. The analog voltage that we want to convert goes from 0 all the way to the positive reference, or not 0, from the minus reference all the way to the positive reference. Then it's a very straightforward logic circuitry to convert that type of decoding to the actual digital value. So, and we'll see that next. And we'll see the details of the circuits as well. But that's basically how it works in general. From the thermometer, the 64 possible thermometer inputs into the logic that comes afterwards, we can then map it to the 6-bit binary value with a lookup table, or what is called a PLA, which is really a lookup table logic circuit. So this is basically the architecture. We have the resistor ladder and the comparators. We hold that outputs of the comparators. We then put it through NOR gates that are going to start converting that thermometer input through the PLA, which is the lookup table, into the 6-bit digital output. That's basically the architecture. So let's look at some circuits. First, the comparator circuit that also has the built-in register. So essentially we see, so each of this is is going to have the sample. So essentially, if we go back, this, even though is shown as 1, is actually replicated and built into the comparator. So the clock and the holding is built and replicated, but this is an abstracted view of the A to D. And that piece here, the sample and hold, is here with the capacitive sampling, and then we have sort of a latch here with the capacitance, and then we basically buffer it out, what we call a Q and Q naught outputs. So that's the comparators essentially. That output goes this circuit, and that's one of them only, okay? And I'm going to go back and show at the input what corresponds to what. The reference is what goes into the minus input from the resistor ladder. The clock is used for the sample. The input is the actual input. And then what we get is really into here. That Q and Q naught is basically at the output of the register part, right at the input of the NOR gate. So again, you have to look at both diagrams together. But here's the connection from the resistor ladder. This is the clock. This is the actual input. This is another clock. All these are clocks, or these are just the clocks. And then this goes into the NOR gates. So this is the sample and hold, comparator, and register all together. For 1, we have 64 of this, or 2 to the n, where n is 6. We have 64 of this. Then when we go into the NOR gate, this is the NOR gate. So the NOR gate, now if the NOR gate is 0, then these transistors are off. And this output is pull up, which inverts then the outputs. This will get the 6 bits. This is the logic. This is the lookup table. And depending on how we program these transistors, we place them, we can get the right lookup table to get from the inputs of the 64 NOR gates to give us the right digital value. So we have, in front of the 64 NOR gates, we have this 64 Q and Q naughts. So each NOR gate is going to correspond to the circuit that we just saw. Now this input is going to be tied to the Q naught of the one below, the Q naught of the circuit that corresponds to the NOR gate, and to the Q above. And by doing that, we're going to be able to detect where the break on the thermometer is. And then we know which range of the analog range we have, and what is the, through the lookup table, what the digital value is. So let's say that the digital logic is such, like so here, okay? So we're going to have 110. So that means that Q naught is going to be 0. Q naught is going to be 0, and Q here is going to be 0. So we get a 1 here. We get a 1 here. And then this transistor turns on, which pulls this line down, which gives us a 1 in this line. But again, this is just an example how the circuit works. The actual transistors are missing, but the point being is that by connecting the NOR gates in this manner, you can detect where the break of the thermometer is when it switches from 1 to 0, and at that point you get the appropriate digital value. It's actually that simple. And then I also have to show a floor plan of the A to D. So here we have the resistor strings, 64 comparators and registers, which is, you know, the NOR gates here, also called term gates, and the PLA, which is the lookup table. Then here we have some output buffers and the clock drivers. So basically that's the floor plan of the A to D. And if we look at a 2-bit section, we can see the resistor strings here. We have the sampling and the input switches. We have the capacitors. We have the other gates, the transmission gates, so the registered, so that, that's a partial cell layout that corresponds more with the comparators and capacitor sections. And the only interesting thing to note here is that in here, this capacitor is sandwiched between metal 1 and metal 2, so it's rather large. If you had 2 layers of polysilicon, then that would make for a better capacitor, and they would be smaller to achieve the same value. That's kind of an interesting observation. And then this is a picture of an actual fabricated chip with that analog to digital converter, and you can see that those circuits have been turned on their side, and here you can see the resistor ladders. There should be 64 of them, with the capacitors and the latches and the comparators. And here you have the NOR gates, and here, and finally the PLA on this side, and then you have some output buffers and the clock drivers and so forth. And you can see here also the bottom reference voltage and the top, and you can see also the input. This is the top reference voltage, and you can see the input here in that line there. All right, so now I want to go back and discuss project number 3. Project number 3 is essentially implementing that phase lock loop that I discussed. So it's basically the same circuit. And since there is a recording of this, you can go back and listen to it again. You can ask questions and so on. But we are going to be implementing this as a group. The whole class is going to be working as different teams implementing different parts of this. So again, we have the phase detector. Important thing is these numbers refer to the, well, actually, let me make this larger. Okay, so yeah, so we're going to be implementing this this phase lock loop or frequency synthesizer. Then we have the phase detector. So remember, this refers to minimum minimum width transistors, minimum channel length, 150 nanometers, but the length of the transistor, the width of the channel for the N is 8 times 150 nanometers and 16 times 150 for the P channel. And then when you implement all these gates, and remember that these NAND gates have a number equal to the number of inputs of N transistors in series, and this input would be to the one that is closest to ground in the series stack. That's what the bubbles mean. Then we also have the charge pump. So we have the charge pump. Went through that. So remember that this refers to multiples now for the gate width or the channel length in terms of 150 nanometers, and this is the gate length or channel width. So it's a different meaning that the numbers that we see when when they are by transistors is different than the number that we see when they are by the gates. For gates it's about N and P. Here is width and length of the channel in terms of the minimum width, which is of the poly, which is 150 nanometers. So those are the circuits. Then we have the filter, here again, W and L of the channel in terms of 150 nanometers. Remember that this needs to be for the appropriate aspect ratio. You have to use the appropriate number of fingers for those big transistors. And then we have the VCO. Same, 150 nanometers because this is one, and this is and the width of the channel is 16 times 150 nanometers. So the idea here is that there are going to be 6 teams to work in each of the pieces. The key is that each team that is doing a piece has to give, as soon as you capture the schematic and you test it, and I'm going to talk about how you test each of the pieces, as soon as you have that, you have to give it to the top level design and layout team. And in the meantime, they will be actually setting up everything so they can drop your databases in there when you have them. But first, before you do any layout, you have to capture the schematic and test it, make sure that it works, pre-layout, and then give it to the team so they can test everything pre-layout. And then when you have the layout, you basically refresh the handout to the top level team. They put everything together and test it again. And time is of the essence. Of course, I'm going to be designating what the teams are and the timelines in an email that I'm going to be sending. So the thing is, when you have your circuit and do your test bench, how do you test each of these pieces? Okay, So let's talk about the phase detector. So all you want to set up for the phase detector is some phase difference between these two signals. And what you should get, whether this signal is behind this one or this signal is ahead this one, you want to get the appropriate width on the up output or the down output. They're both positive pulses, but they won't happen if depending on the relationship of these two signals of the edges, you're going to get the up or the down pulse. Very simple test. Okay. For the switch of the charge pump, you're going to be applying pulses. Pulses. Put some capacitor here, and you're going to be applying pulses and up or on the down, and then you should see the current charging the capacitor or discharging it, and the voltage here should be a ramp, up or down ramp, and that's how you know that it works. It's that simple. So for the filter, you're going to be applying current sources that you're going to apply a pulse of current, positive or negative. So either you're charging or discharging, and again, you should see a ramp here at this output, and that's how you test your circuit here. Very simple, but the key here is for it to come together fast and efficiently, and the communication between the teams that are doing these pieces and the team that is doing the top level. Then finally, the VCO. The way to test the VCO is to sweep with maybe 10 different values from 0 to VDD, which is 1.8 volts. Sweep the voltage here, and then measure the frequency that you get out of the oscillator here. And then you can plot in Excel frequency versus voltage, and you are going to see that you're going to get some type of S-curve that is tilted, but there is going to be a good region of linearity in the middle, and that's the useful operating range of the phase lock loop from a frequency perspective and output frequency perspective. I am not requiring very complex handouts or handoffs or deliverables actually. I just, each team is going to have a report, and as you know, I made this due at the very last end of the semester. I just need the schematic, the layout, waveforms of your tests, pre and post layout, and a module symbol and subcircuit that you use to test. That's it. That's it. There's no real, you give me that with a cover sheet in your PDF report hand in, and we'll be all set. And again, I'll be available for questions via email and during times where I'll be in Zoom to answer your questions. So that is what I wanted to cover in this video.